the internal energy enthalpy and specific heat of ideal gas. In general, for any substance, the internal energy U depends on the two independent properties specifying the state. Depends on two independent properties specifying the state. For a low density gas, however, U depends primarily on T and much less on the second property P or V. For a low density gas, U depends on primarily on T, temperature, and much less on the second properties such as P and a specific value. For the low density gases, for example, consider several values for superheated vapor from table B13 that's shown in this picture and table. For example, the internal energy for superheated vapor at the various pressure at 20 degrees temperature, at 10 megapascal, kilopascal, we have the 2661 kilo of the internal energy, kilojoule on kilogram, for example, maybe. As you can see, the change in the internal energy in the pressure increase is not too significant, but also in the temperature increase we have significant change during the temperature increase. So for the low density gases such as superheated vapor, we have internal energy is a function of temperature. From these values, it is evident that the relation of the temperature and internal energy. We note that the dependence of U on P is less at low pressure and is much less at high temperature. That is, as density decreases, so does dependence of U on P or V. It is therefore reasonable to extrapolate this behavior to very low density and assume that as gas density becomes so low that the ideal gas model is appropriate, in this case for low density gas, ideal gas appropriate. So we can write for an ideal gas that we have and only. The relation between the internal energy U and the temperature can be established by using the definition of constant volume, specific heat from the previous lesson. We have from T at P constant. Because the internal energy of the ideal gas is not a function of a specific volume, for an ideal gas we can write the exact differential, it is du on dt, or du equals to Cv0 d temperature, where the subscript 0 denotes the specific heat of an ideal gas. Subscript 0 denotes the specific heat of the ideal gas. So we can write T temperature for an ideal gas. We repeat ideal gas is or low density temperature, low density gases. From the definition of enthalpy and the equation of state of an ideal gas, it follows this relation. And we have P equals to RT. So H is RT and also is a function of temperature. The relation between the enthalpy and the temperature is found from the constant pressure specific heat, where Cv Cp equals to or for an ideal gas dH on dt, and we can write dH Cp0 d temperature and dH mCp0 dt. It is the specific heat for ideal gas Cp0. So we have two relations here. For the internal energy, we have CV dt and dH Cp dt, low density gas. The consequence of these two equations are demonstrated in this picture. Shown in this picture, which has two lines of constant temperature. This line and this line. Since internal energy and enthalpy are functions of the temperature only, these lines of the constant temperature are also lines of constant internal energy and constant enthalpy. As shown, constant temperature at the process in the also constant temperature. However, regardless of the path, the change in internal energy is the same as the change in enthalpy. Four lines of constant temperature are also lines of the constant internal energy and constant H, as shown here. This means that, for example, because the internal energy and enthalpy of an ideal gas are function of temperature only, it follows that the constant volume and constant pressure specific heats are also function of temperature. So we have also a constant temperature. Because of all gases approaches ideal gas behavior as the pressure approaches to zero. So when the pressure approaches zero, all gases, the gas behavior is as ideal gas. The ideal gas specific heat for a given substance is often called the zero pressure specific heat. The ideal gas specific heat for a zero pressure heat for the ideal gas specific heat. And the zero pressure constant pressure specific heat is given the symbol Cp0. The zero pressure constant volume specific heat is given the Cv0. Zero pressure specific heat at constant volume at zero pressure specific heat at constant pressure equals to ideal gas specific heat coefficient the values quantities the various amount of the Cp0 as a function of temperature for a number of substances shown in this picture. These values are determined by the techniques of statistical thermodynamics. And will not be discussed here. A brief summary presentation of this subject is given in Appendix C. Please note there that the principal factor causing a specific heat to vary with the temperature is molecular vibration. More complex molecules have multiple vibration modes and therefore show greater temperature dependency, as seen in this picture. This is an important consideration when deciding whether or not to account for a specific heat variation with temperature in any particular application. A very important relation between the constant pressure and constant volume specific heat of an ideal gas may be developed from the definition of enthalpy. A very important relation between specific heat, constant pressure, and constant volume specific heat for an ideal gas. The zero is denotes the ideal gas. Can be obtained from the enthalpy relation. The enthalpy relation is HU plus work PV equals to, for the ideal gas, U plus RT. Cp0 dt plus R dt. So Cp0 minus Cv0 equals to R with negative dt from this relation. On a mole basis, Cp0 minus Cv R. These tell us the difference between the constant pressure and constant volume. The specific heat of an ideal gas is always constant, though both are function of temperature. Thus, we need to examine only the temperature dependency of one, and the other is given in the related equation. Values of the specific heat at room temperature, and gas constants for various gases are given in table A4 and F4. Table A4 and F4. Let us consider the specific heat Cp0. There are three possibilities to examine. The situation is simplest if we assume constant specific heat, that is no temperature dependence. Then it is possible to at first constant specific heat. So we can write, for example, dHCp0 dt H2 minus H1 Cp0 T second T1. It is noted that the circumstances under which this will be accurate model is dependent on the substance and material. It should be added, however, that it may be reasonable approximation under other conditions, especially if an average specific heat is in the particular temperature is used. Values of a specific, as we said, are tabulated at room temperature, table A4 and F4. The second possibility for a specific heat is to use an analytical equation for Cp as a function of temperature. Cp is a function of temperature because the result of a specific heat, so H2 minus H1 equals to Cp0 as a function of temperature dt. Because the result of a specific heat calculation from statistical thermodynamics do not lend themselves to convenient mathematical forms, these results have been approximated empirically. The equations for Cp0 as a function of temperature are listed in table A6. Values Cp T function tabulate. The third possibility is to integrate the result of the calculation of a statistical thermodynamics from an arbitrary reference temperature to any other temperature T and define a function. Integrate the results of the calculation of statistical thermodynamics from an arbitrary reference reference temperature, T, and to define as a function ht t0 dt. This function can be then tabulated in a single entry table. Then between any 2 points we have this relation T0 T1 HT second HT1, and it is seen that reference temperature cancels out. This function ht and a similar function ut is listed for air in table. The function ht cp0 dt and ut or ut equals to ht minus rt, tabulated in the table for A, table A7 and F4. Table will frequently used in the problem solving. These functions are listed for other gases table AX and A6. Give us the most accurate answer, but that the equation in table A6, for example, would give a close empirical approximation. Constant specific heat would be less accurate except for non-atomic gases and gases below room temperature. Constant specific heat would be less accurate except for monoatomic gases and gases below room temperature. It should be remembered that all these results are part of the ideal gas model, which in many of our problem is not a valid assumption for the behavior of the substance. There are various problems related to this section. The next section is the first law as a rate equation.